Now, for the second theorem in systematic random sampling, we have to prove that variance of y bar n is greater than or equals to variance of y bar systematic random sampling. We will, I already told you in the before video that for this variance, we'll be using n minus 1 s square by n minus k into small n minus 1 by capital N s square WSY. We are not going to use the generalized form. We'll use this form just so it is basically easy to prove this theorem. And we are also proving it with this. So let's write the formula. Variance of y bar n, which is also SRSWOR by the way, is equals to n minus small n by capital N s square by n. We can also write this n inside. That's what we will do in the further steps. All we have to do is variance of y bar n minus variance of y bar systematic. That's all we need to do. There's nothing more to this. That's all we need to do. So variance of y bar n minus variance of y bar systematic. That will make it won't fit here, so I'll just write it here. That is n minus n by n into small n. I'll write the small n term inside. S square minus n minus 1 s square by n minus k into n minus 1 s square WSY by n. If we take this minus inside, this will become plus. So n minus n capital N into small n minus n minus n s square plus k into k into n minus 1 by capital N s square WSY. All I did was just add this minus, multiply this minus inside. That's it. So this term became negative and this term became positive because there's a minus in between. Now in both these terms we can see that s square is common. We can take s square as a common term and s square into n minus n n minus n minus 1 by n plus k into n minus 1 s square WSY. And we already know that n is equals to nk. So we can basically write this capital N in the form of small nk. So that we can it's basically just to cancel this k. That's it. That's why we took it like that. Now we need to solve this inside. The LCM would be we need to multiply small n in both the numerator and the denominator in the second term. That's all we need to do. S square n minus n by n into n minus, this will become n plus small n plus n minus 1 by n s square WSY. And then if we can see that we can cancel this term out. You can cancel both these terms. Now s square into here, if we take n common, from here, if we take this capital N common, then n into 1 minus small n by n into another n. So this both the n's will cancel and plus n minus 1 into n s square WSY. Here I made a small error. I'll just cut the entire thing out. I made a small error. I'll take minus n out. If I take minus n out, then this will become n minus 1 by n. Capital N2. Now we can cancel out the n's plus n minus 1 n s square WSY. We will see why. I'll tell you why I rectified this mistake. If I were to do this, then we couldn't really prove what they asked us for. We can't really prove this. That's why I had to change it. That's why we have to take minus n as the minus capital N as the common term, not simply just capital N, and we can't write it like this. That's it. Now they should make it minus s square, because the minus 1 is completely multiplied here now. So minus s square n minus 1 by n plus n minus 1 by n. Here also it is like this, and WSY. If we can take n minus 1 by small n as the common term, n minus 1 by capital N, s square WSY minus s square. Now, this term is obviously greater than 0. However we look at this term will be above 0. In any way, it will become 0. So, this entire term is greater than 0. Then, now we can prove what we were already asked for. So, this would become y bar n minus variance of y bar systematic random sampling is greater than 0. Is greater than or equals to 0. This could also equal 0, by the way, because of this term. It could also equal 0. So if we just send this term to the other side, then variance of y bar n is greater than or equals to variance of y bar systematic. Variance of y bar systematic. Also, we can also prove this one. So if we send this entire term to the other side, then this would just stay as s square WSI minus s square greater than or equals to 0, and s square WSY is greater than or equals to s square. These are the two proofs required for this theorem. That's it.